Hello, my dear students. Good afternoon to all of you. Am I visible and audible? If I'm visible and audible to you guys, can you let me know the answer in the chat box? Just give me a thumbs up or type yes in the chat box if you can able to hear my voice and if I'm audible, visible and audible to all of you, so that we can proceed. Students, am I audible and visible? Please give me a reply in the chat box. Let me know the answer in the chat box. Can you able to see me and hear my voice? Yes. Okay. Okay, fine. So now let's continue with the coordination compounds lesson. Okay. So in the previous class, we have discussed about the Burners theory and classification of coordination compounds and some of the ligands classification we have discussed, right? So now moving forward with that, I have got a previous year question for you to have this as a recall test. Okay. So this is the question based on the classification of ligand. Okay. So under the classification, we have studied the first classification is based on the charge. Second is on the basis of density. Third is I have discussed about ambidentate and chelating ligands, right? Yeah. So now tell me which complex compound is most stable. Which complex compound is most stable? So Vicky has given option 2 as the correct answer. So what about others? What about others? What about others? Is option 2 the correct answer or it is wrong? What about others' opinion? Just look
Maybe
at.
option 2.
Sorry,
Option 2.
option 2. Who is that? Who gave me this answer? May I know the name? Just a second. Sorry for the thing. Yeah. So one person have said option 2 as the correct answer. What about others? So I'll go for the answer. Option B or option 2 is the correct answer. Very good, Vicky. Vicky, can you give me the reason why option 2 is the correct answer? Can you tell me why option 2 is correct? The explanation part. Sorry?
Crystalline diamine.
Sorry, my dear, I'm not able to hear you. Just give me the answer in the chat box, okay? Your voice is breaking. Yeah. JNV North and Middle Andaman students. In the previous class, I told you that a particular complex compound will be more stable. Yeah. If we have a chelating ligand inside the coordination entity. Okay. So now with this concept, you see this question. In the first option, we have two different ligands. One is NH3 and the other one is NO3. Both of them are monodentate. Okay, only one donor site is present. If you come to option B, we have two types of ligand. One is Cl and the other one is En. So who is this En? It is a bidentate ligand. So if a bidentate ligand is present, then it is also called as a chelating ligand, I told, right? It is a chelating ligand. So this chelation will give the more stability to the complex. Okay, so the chelating ligand containing compounds are more stable in nature. Okay, that's why option B is correct. When you come to option C, again we have monodentate ligand NH3 inside the coordination entity. And when you see for option D also we have NH3, H2O and Br. All the three types of ligands are monodentate ligands. Okay, so that's why option B is the correct answer. So can you all able to understand now? Yes. So all of you can able to understand, I think. So now let's go for the today's topic. Okay. So today we are going to study the nomenclature, isomerism, and if time permits, we will discuss about the valence bond theory also. Okay. So moving on to chelation. JNV North and Middle Andaman students, chelation means ring formation. I have explained this in the previous class itself, but no problem. I will just give you the gist of it now. Okay. Chelation means a ring formation. So ethylene diamine is a bidentate ligand, means it has two donor sets. So if that particular ligand forms the bond, coordinate bond with the metals, of course, this is my metal atom. Okay. And the formula for ethylene diamine is CH2CH2, NH2, NH2. Okay. So this is one ethylene diamine molecule. One ethylene diamine is having two donor sites. So if they donate, if the nitrogens donate the electrons to the metal, it forms a 1, 2, 3, 4, 5, 5-membered ring, right? So it is a ring formation thing we are getting. So the ring forming ligands are called as chelating ligands and they provide the stability to the complex in the aqueous solution. So that's why that is more stable and it is called as chelating effect. Clear and all right now? Any doubt? Is it okay? Shall I proceed with the nomenclature? JNB North students, North and Middle and Andaman students, shall I proceed? Yeah, okay. So let's go for the nomenclature. So first, let us see the naming of the mononuclear coordination entities. Okay. No, my dear, NO2 doesn't show the chelating effect. NO2 is an ambidentate ligand and it is not a chelating ligand. Okay. So there is a difference between ambidentate and chelating, like chelation, right? Ambidentate means two different donor site will be there, but at a point, at one time, only one can donate. Either nitrogen will donate or oxygen will donate. Both of them cannot donate at the same time. But in case of chelating ligand, two donor sites can be present for one particular ligand and both of them can donate at a single time. Clear? Clear? Is it clear now? NO2 is an ambidentate, but ethylene diamine is a chelating. Okay, fine. So now let's go for the rules that we have to follow to name a coordination compound. So rule number one is cation is named first in both positive and negative charged coordination entity. So let me take a complex. So all of you see here. So this complex is starting with K4, which is potassium. means that first ion is a cation. So here potassium is a cation. So we have to start the name with potassium. Okay, and hexacyanoferrate is the name of the anion, which is nothing but the coordination complex. Suppose instead of this, if I take this compound. So here the compound is starting with the coordination entity, means that coordination entity is the cation and Cl2 which is present outside is the anion. So we have to name the cation first. So the complex is named first. Pentamine, chlorido, cobalt is the name of the complex, and the chloride, the anion is written later only, next only. Okay, is it clear for all of you? So this is rule number 1. Next, coming to rule number 2, ligands are ligands are named according to alphabetical order and before the name of the central atom or ion. Okay, ligands are named according to the alphabetical order. So when do we follow this rule? If we have more than one type of ligand in the complex. So you see here, we have NH3 and Cl. So two different types of ligands are present inside this. So this NH3 is called as amine and Cl is called as chlorido. Okay. So now if two ligands are there, we have to follow the alphabetical order. So A comes first in the alphabet, right? So that's why we are going for amine first. So how many amine we are having? 5 amines we are having. So the name is penta. For 5 we have to use penta, right? So penta amine. Then chlorido. Cobalt is the central metal atom. 3 is the oxidation state. And at last you have to put chlorine. Okay. For NH3 we have to amine, use amine, and for Cl it is chlorine. Okay. Clear? This is rule number 2. Now coming to rule number 3. So any doubt from the first two rules for anyone? Shall I proceed with the third rule? Just give me the reply first. Yes. Thank you, Sneha. So coming to the third rule. The names of anionic ligand ending with O, those of neutral and cationic are the same except for aqua for H2O, amine for NH3, carbonyl for CO, and nitrosyl for NO. Okay. If the ligand is anionic, okay, if the ligand is anionic, then we have to use the suffix O. So this thing we have already discussed in the previous class, right? When I was discussing the classification of ligand, I told you. But if H2O or NH3CO NO is present, then we should not use the name which ends with O. We have to use aqua for H2O. Okay, here I have 6 water. This is a cationic complex. All of you can able to see the cation, right? This is a cationic complex, but it has H2 as the ligand. So it should be named aqua. So hexa aqua copper 2 ion is the name of the complex. Okay. Now coming to rule number 4. Prefixes for monodentate ligand should be mono, di, tri, tetra, penta, hexa, etc. Okay. So when name of ligand already include the numerical prefix, then you have to use bis, tris, tetrakis, etc. Suppose in this complex, if I take this complex, I have 6 ligand. So 6 means what I have to use? Hexa. Okay. And Cn is called as cyanido. Right? Cn is called as cyanido. So we know that we have to start the name of the complex with potassium because that is the cation. So what could be the name of this complex? Potassium hexacyanidoferrate 3. Potassium hexacyanido. No. It is not iron Nagastri. It is ferrate. Okay, I told you, right? If the complex is anionic, then you have to use the suffix ate. I'll come to that rule. Okay. You are not able to see the other color except white. Why it is like that? Is it the same for all students? Can you all able to see the green color, yellow color thing which is there on the slide? All of you can able to see or is yes, yes. Then I think there is some, oh yeah, then I think there is some issue with JEE Ahmedabad students. Just look into your issue. Just look into your issue because all others can able to see. Just see to the brightness of your screen from which you are seeing the class. Okay. Okay. So now I'll proceed. Yeah, if the complex is anionic, anionic means it will be present there secondly. Okay. If it is anionic, then you have to use the suffix at. For iron, it is ferrate. If some other is there, some other means if the aluminium is there, then I have to use aluminate. If nickel is there, I have to use nickelate. Okay, so if the complex is anionic in nature, then we have to use the suffix at. Got it? I'll take one more example. So in this example, the name of the two ligands are one is chlorido and the other one is triphenyl phosphate. So this is called as triphenyl phosphate. Triphenyl phosphate. So this triphenyl phosphate is given twice. So already the name of the ligand includes tri. So again you should not use by here. So that's what the second line says. When the name of the ligand already includes the numerical prefix, then bis. See, nothing to worry, my dear JNV Ahmedabad students. It is not your called kind of thing. It is just might be a technical issue. Okay, so it is not your fault or mistake. Just look into your uh, system. I don't know whether you're watching from mobile or from the screen in your classroom. I don't know. Just turn off and turn on and see whether you can able to see or not. Okay, clear? Or else from next lesson onwards, I'll try to change the background of my PPT which I'm using so that it won't be an issue for you. Okay. Yeah. So all of you can able to understand this fourth point, right? So the ligand name already includes tri. So we have to use bis to denote this two. Okay. So I'm having two chlorido and two triphenyl phosphine. So here we should not use di. Here we have to use bis. Okay, and this is a neutral compound. So the nickel is named as such as nickel. There is no nickelate or some other thing. Nickel is named as nickel because it is neutral complex. Okay, I'll take one more example. So here you see we have three ethylene diamine. And IUPAC name for ethylene diamine is ethane 1,2 diamine. This is the name of the ligand. And this name has 1 and 2. This name already has the numerical prefix. So what I have to use to denote this 3? I have to use tris. It is not tri, it is tris. Okay. So tris ethane 1,2 diamine. Now for Fe you have to use iron. Why in this case I am using iron? In the first case I am using ferrate. Because in the first case potassium is the cation and this complex is the anion. Now in the last case, complex is the cationic complex. The coordination entity is cation. If the coordination entity is anion, sorry for the interruption. Uh, yeah, if the complex is anion, then you have to use this ferrate. You have to end the name with ATE. If the complex is cation, you have to name the metal atom as such. Okay, if the complex is cationic or if it is neutral, you have to name the metal as such. So in the second case, it is neutral, right? No charge is present. No counter cation or anion is there. So it is a neutral compound. And the third example is cationic. So for these two cases, metal atom should be named as such and that's why Fe is written as iron. Is it clear for all of you? Shall I go for the next rule? Any doubt? You want me to show the previous slide? Okay. Okay, I'll show you. Take a snap of it soon, okay? JEE rowing students, just take a snap of it first. Let me know once you're done with it. Finished? Okay, very good. What about the slide? Completed? I'll erase the things which I have written. Is it done now? Shall I go for the next? Yes. Good. Now coming to the fifth rule. The fifth is about the oxidation state. So the oxidation state of central atom should be written in Roman numeral in parenthesis. Roman numeral in parenthesis. Nickel contain +2 and then phenyl, anything like that. I am not getting what you are trying to ask, my dear. So can you explain me in a little bit brief manner? Okay, okay. You are asking me about the oxidation state of the triphenyl phosphine. Is it like that? Yeah. Triphenyl phosphine is a neutral ligand. So we have discussed this in the classification of ligands. So the charge is 0. Okay. For triphenyl phosphine, it is not phenyl actually, it is triphenyl phosphine. It is a neutral ligand, so the charge will be 0, like H2O, NH3. Okay. Clear? Very good. Yeah, this point is very easy. We have to write the oxidation state in a Roman numeral form in parenthesis. Okay. So this is the oxidation state. You know how to calculate the oxidation state, right? All of you. So I'll do for one. Okay. Triphenyl phosphine, that PPH3 ligand, my dear. So that PPH3 ligand we have seen in the previous slide, no? So this is called as triphenyl phosphine. Phosphine means PH3. Okay, PH3 is called as phosphine. If all the three hydrogens are replaced by three phenyl group, then we are calling this as triphenyl phosphine. Okay, clear? PPH3 is called as triphenyl phosphine. Now coming to the oxidation state of iron. So iron is taken as X. We have 4 potassium and for each potassium the charge is +1. 4 potassium means +4 plus X, and for each cyanide it is -1. We have 6 cyanide. So it is -6, which is equal to 0. X is equal to 6 minus 4 and X is equal to +2. Okay. Clear for all? So +2 is the oxidation state of iron. That number 2 has to be written in a Roman numeral form inside the bracket, curved bracket, which we call as parenthesis. Okay. Clear for all? Shall I go for the next point? Shall I go for the next point? Yes. So coming to point number 6. If the coordination sphere is cationic or neutral, then metal atom is written as it is. Otherwise, AT suffix is added to the metal name. So this point I have discussed with you in the previous slide itself. If the coordination sphere is cationic or neutral, then you have to use the suffix AT. Otherwise, it is written as such. So here in this case, the coordination sphere is anionic, right? It is not cationic, it is anionic. Potassium is cation. So we have to name the ion as ferrate. Okay. And in this case, it is neutral. So if it is neutral, then it is written as it is. So nickel is written as it is as nickel. Okay. If it is anionic, then you have to use the suffix ate, right? So for iron, we are using ferrate. And for silver, you have to use argentate. For gold, you have to use aurate. And for Fe, it is ferrate. And for nickel, it is nickelate. Okay. And for cobalt, it is cobaltate. So like that, we have to use the suffix ate for anionic complex. Okay. This is all about the sixth point. And these are the six rules which we have to keep in mind to name the coordination compound. Okay. Now shall we go for some questions? Are you all ready to give me the answer for the questions? Shall I go for the complex? Will you name? Yes. So I have taken three questions. Okay, three names. You have to give me the formula for these three names. So the first is tetraamine diaqua cobalt 3 chloride. So this one I will try. For the second and third complex, you try. Okay. So how to take the formula from the name? Tetraamine. Tetra means 4. Right? So how many amine? Tetraamine. Amine is NH3. I have 4 NH3. And diaqua. Aqua means H2O. And how many H2O? Di. 2 H2O. Cobalt is the central metal atom. So right here. Okay. And put the bracket. Because oxidation state is coming. No. Oxidation state means the complex is ending there. Yeah. Sneha, are you sure that we have only one chlorine outside the bracket? Are you sure? So this is the complex. So let me try. You check whether your answer is correct or not. Okay. So students, so this is a coordination entity, and outside the bracket we have chloride. Chloride means it may be 1Cl or 2Cl or 3Cl outside the bracket. How to know whether I have only 1Cl or 2Cl or 3Cl? By looking into the oxidation state only, you can find out that. Okay. So oxidation state is 3. Oxidation state of the metal atom is 3. So amine is neutral, so 0. Water is also neutral, so 0. Only if I put 3Cl outside the bracket, I will get the oxidation state of metal atom as X plus 0 plus 0. And for each chlorine minus 1 charge, right? So 3 chlorine. So minus 3 equal to 0 and X is equal to plus 3. And this plus 3 is the oxidation state which is given here in the question. So there should be 3Cl outside the bracket like this. Clear? Even if we have 2Cl outside the bracket also, the name will be chloride only. For 1Cl also, it is chloride only. Because it is a counter anion which is present outside the bracket. If Cl is present inside the bracket, then we can use bi, tri, tetra, like that. Okay. If it is outside the bracket, chloride is chloride. That's all. That's all. 2Cl or 3Cl or 1Cl, that doesn't matter. Clear? So the name of the formula for the complex is CO, NH3 4 times, H2O 2 times, and Cl3. Clear for all of you? Shall I go for the next? Can you guys try the answer for the second subdivision? Yes. Okay. Potassium tetracyaninonickelate. So find out the answer first. Give me the answer in the chat box first. Yeah, Ahmedabad students. Just by looking into the oxidation state, you have to find out the number of chlorine. Okay, inside the bracket, I have NH3 and H2O. Both of them are neutral, so 0. So only if I put 3Cl outside the bracket, Oxidation state of the metal can be +3. I'll explain for the second compound, that time you can understand better. Okay, I'll explain the same thing here in the second solution also. So all of you are getting K2NiCN4. Okay. Okay, now let's check whether this is the correct answer or not. So you see, potassium tetracyanidonicolate. So there is a gap between these two names. Means potassium is the cation. Okay. So let me put K. I don't know whether I have 1K or 2K. 2K means K2 or K3 or K4, etc. I know that potassium is present. That's all. Okay, how many potassium? I can calculate that from the oxidation state only. So now let me proceed with the coordination entity. Tetracyanidone. CN is the ligand, cyanidone is the ligand, and I have 4 cyanidone, and the metal atom is nickelate. Metal atom is nickelate. So this is the coordination entity. And the oxidation state is given as 2. So we are going to find out the oxidation state of this metal. And it is actually 2 given in the question. And we know that cyanide is a anionic ligand. So Cn minus. So minus 1 for 1 Cn. I have 4 Cn. So 4 into minus 1 is minus 4, which should be equal to 0. And I have potassium here. So if I put 2 potassium, then for each potassium it is plus 1, right? K plus. It is a first group element. So K plus. If I put 2 potassium, then I will get plus 2 plus x minus 4 equal to 0, and x is equal to 4 minus 2, which is equal to plus 2. And this is the thing we are getting here. Is it clear now for all of you? So that's why the formula is K2NiCN4. All right. ZB Ahmedabad students, can you able to understand? Yes. Okay. Okay. So now let's go for the third compound. Find out the answer for this. Tris ethane 1,2 diamine chromium 3 chloride. What could be the name? Find out fast. Find out fast. Has anyone got the answer? Nagashri, what is this 3? I need the complete answer. Yeah, complete formula is CREN thrice. Yes, very good. JNB Adam students and Priyanka has got the correct answer. JNB Cockroach also got the same thing. Sneha, yeah, many of you have got the correct. Now, how this is? Why suddenly Bhagat is giving me the wrong answer? Bhagat, see, we have tris ethane. No, tris means 3. So we have 3 ethylene diamine. Okay, tris. So En is the ethane 1,2 diamine. I have 3. Chromium is the metal. And outside the bracket, I have chloride. Oxidation state is given as 3. So now I have to check the ligand. The ligand is ethylene diamine or ethane 1,2 diamine, which is a neutral ligand. So it will be 0. Okay. And chromium is taken as X. X plus 0. And if I put 3Cl, then I will get minus 3, which is equal to 0. And X is equal to plus 3. So the oxidation state of the chromium is coming out to be plus 3. Clear? So this is the correct answer. Can you all able to understand? Is it okay? Any doubt? Shall I proceed with the next question? So in this question, I have given you the name and I have asked you to find out the formula. Okay. In the next question, I will give you the formula. You have to find out the name. So for the first complex alone, I will find out, and from the remaining thing onwards, you find out. Okay. So if a complex formula is given and if you are asked to find out the IUPAC name, what is the first thing that we need to do? The first thing that we need to do is find out the oxidation state of the metal. So the metal is cobalt, X, and we have amine ligand. It is a neutral ligand. So Z is neutral. So what we have to do is find out the oxidation state of the metal ion like this. So many people have got the answer, but anyways, so let me explain this so that all can understand. Okay, very good, Priyanka and Sneha. So I have found out the oxidation state as +3. Now start the naming. So how to name? Cation has to be named first. So here the complex is starting with the coordination entity, which is the cation. So from that, I have to start with the ligand, right? I have 6 amine ligand. So it is hexa, amine, cobalt, 3, chloride. Hexa, amine, cobalt. 3. See, all of you are making mistakes in the 3, in the oxidation state. You should not use this numerical 3. Okay, we have to use the Roman numerals. All of you see Sneha and Priyanka's answer or the answer which is there on the slide. We have to use the Roman numerals, right? This 3 you have to use. The other 3, that number 3 is incorrect. Okay. Maybe because of the typographical error. Jabrun Sultana, Piali and Madhukar Reddy have got. Madhukar Reddy is also using the other 3. Okay. But anyway, no problem. Correct. Okay. Very good, students. I hope you guys have understood how to name the complex. Now I'll go for one more complex. All of you try the name first. Find out the oxidation state of cobalt. What is the oxidation state of cobalt? Is it +3? JMB Kadapa student is saying +3. Yeah, very good, very good, very good. It is +3. Now what is the name? We have 2 different types of ligand, right? One is amine, the other one is Cl. Chlorido, which has to come first? Alphabetical order. Nagashri, it is pentamine, not penamine. I can able to understand, okay? No, just for fun only I'm saying. Yeah, the name is pentamine. Let's wait for others also. Let's wait for others. Let them try. Pentamine. Pentamine, chlorido, cobalt, 3 chloride. Very good. Your answer is correct. Very good, students. So let's go for one last question. Okay, one last compound I'll give you. K3FeCN6. What is the oxidation state of Fe here? What is the oxidation state of Fe? Very good, +3. Again, it is +3. What is the name? What is the name of the complex? What is the name of the complex? Potassium. So you should leave some space between cation and anion, okay? Nagashri, you have to leave some space between potassium and hexacyanide because cation and anion should have some space. But now I can able to understand, no problem. potassium hexacyanide. It is not 3 ferrate. It is ferrate 3. Okay, because the oxidation state is for the metal atom. So you have to put the oxidation state once after you write your metal atom. Okay, ferrate is the metal, right? After that only you have to write the oxidation number. So it is potassium hexacyanide ferrate 3. Very good. Okay, oxidation state is +3. So why ferrate is written? Because the coordination entity is anionic. So that's why we are using ferrate. If it is cationic or neutral, we'll write Fe as iron, IRON. Okay. Yeah. Potassium hexacyanide. Cation should have a single name and anion should have a single name. You should not leave any space between the anion. Okay. This complete name is an anionic name. So now I can understand that all of you can able to write the name if the complex is given, and you can able to write the complex if the name is given. Any doubt from the nomenclature part for anyone? Is everything clear? Finding out the oxidation state, writing the name, everything is clear. So all of you go through the rules once again and try to solve some questions from the IUPAC nomenclature. Okay. So that all the small doubts which you are having will also get clear. If time permits, I will also solve some questions. Yeah. So now let's go for the next topic, which is isomerism in coordination compounds. So isomerism, what is meant by isomerism? Iso means same. Isomerism means some compound molecular formula will be same, but it will have some different structures. Okay. So isomerism is actually classified into two types are there. One is called as structural isomerism and the other one is called as stereoisomerism. Let's discuss one by one. What is structural isomerism? So the compounds having the same molecular formula and different bond arrangement around the central atom are called as structural isomerism. To be more specific and simple, same molecular formula but different structures. That's all. Same molecular formula but different structures. So if it is the case, then it is called as structural isomerism. Okay. Now this structural isomerism is again classified into four. We have four different types under this structural isomerism. They are linkage, coordination isomerism, ionization isomerism, and solvate isomerism. So let's discuss each and every type by having some examples. So shall I start with the linkage isomerism? All of you can able to understand what is isomerism and the types and the definition for a structural isomer, right? Shall I start with the linkage isomerism? Okay. So now what is linkage isomerism? And where do this linkage isomerism arise? So linkage isomerism arises in the coordination compound containing ambidentate ligand. What are ambidentate ligands? The ligands which has two donor sites, but at a time only one can donate. Those ligands are called as ambidentate ligands. For example, thiocyanate. So SCN is the ligand. Here sulfur is donating the electrons pair to the metal, and in this case nitrogen is donating. But the formula is same for both. One is SCN and the other one is NCS. The atoms taking part in this ligand is same. But one case sulfur is donating and the other case nitrogen is donating. So the linking atom is different. So metal is linked with sulfur here. Sorry, my dear students. I am not feeling well actually. Sorry for this. And in the second case, nitrogen is donating to the metal. Okay, so it is called a thiocyanate. So the linked atom is different for both, and that's why it is called as linkage isomerism. Formula is same, but the atom to which the metal is linked is different. A person called Jorgensen, he did an experiment, okay, with the cobalt complex. I'll show you the complex also. This is the cobalt complex. And he found this color change. So both of the compound has the same formula. Cobalt and 5NH3 with the NO2 and Cl2. In the first case, NO2 and the second case, ONO. But the formula remains same only, one nitrogen and two oxygen. But the color that he got for the first compound is yellow. Okay, it is yellow. All of you can able to see the yellow color compound, right? And here it is red. So why two different colors are observed? Because they are isomers of each other. In the first case, cobalt is bonded with 6 ligands, in which 5 of them are amine, NH3, 5 of them are NH3, and the sixth is NO2. So here it is bonded with nitrogen. Cobalt is bonded with nitrogen. But in the red color complex case, again here also we have 6 ligands only. 5 of them are NH3. All the 5 of these are NH3. But the sixth site is occupied by ONO, NH3. This is NH3. And the sixth site is occupied by ONO. Okay. So here cobalt is bonded with oxygen. Here CON bond and here COO bond. So the linked atom is different. So it is called as linkage isomerism. So these two compounds are the examples of linkage isomerism. This type of questions are actually very easy, you know. They will give you the compound and they will ask you to find out the isomerism existing in that. Here, just by seeing the compound itself, we can able to find out, right? So the linked atom is different because it contains ambidentate ligand. So it is an example for linkage isomerism. Very, very easy questions will come from this. You don't have to memorize or understand much here. Okay, if you can able to understand the concept, then it is going to be an easy part. Clear? Shall I go for the second isomerism? Yes. Yeah. The next is coordination isomerism. This is the second classification under structural isomerism. Okay, I don't know what to do from my side. I'll check it out. I'll check it out. Or else you can do one thing, students. JNV Ahmedabad, you can do one thing. You go to YouTube. Okay. You type Avanti Live 2. Okay. Go to YouTube. Type Avanti Live 2. That is a channel for chemistry. Okay. So there you can get this video. So now it is live only. You can get the video there. Just check once whether you can able to see this red color and green color in the YouTube video which is going live now. Okay. So just check it and come back here. Is it clear? So just check it over there and come back. So now let's go for the definition for coordination isomerism. So this type of isomerism arises from the interchange of ligands between cationic and anionic entity of different metal ions. Coordination isomerism means you will have two coordination entity. So this is actually one single compound. So in which the first is the cationic part and the second is the anionic part. Both of them belong to the same compound only. But both have the square bracket. Okay, but they are that is single compound. So this is one compound. This is one compound. Now, if you interchange the ligand, or if you interchange the metal, If the ligand as such and interchange the metal, you will get another compound like this. If the ligand as such and interchange the metal alone. So in place of Cr, you put CO, and in place of CO, you put Cr. So you will get another compound. You will get another compound. And these two compounds are the examples for coordination isomerism. Okay, so just change the metal atom alone, you will get another pair, and those two are the examples of coordination isomerism. Very, very easy. Clear? Shall we go for the third one? Third type? Shall we go for the third type? Yes? Yeah. The third type is ionization isomerism. So what is this? When counter ion in a complex. What is meant by counter ion? The ions or the elements which is present outside the bracket. Okay, if it is present right side to the bracket, it is called as counter anion. If it is present in the left side, it is called as counter cation. When that counter ion in a complex is itself a potential ligand and can displace a ligand which then become a counter ion, then it is called as ionization isomerism. If you are by looking into the definition, you may think that it is something different, but don't worry. If you look into the example, you can understand that it is a very simple thing. Okay, so this is the complex. Okay, and here I have bromine outside the bracket, which can act as a potential ligand. Okay, so I can put this bromine inside and SO4 outside. If I put like that, I will get another complex like this. No, now this SO4 is a ligand and it becomes counter ion after displacement. So what I have done, I have put this inside and put SO4 outside, and I have got another compound. Now these two compounds, this is the first compound, this is the second compound. So these two compounds are the examples for ionization isomers. They are called to be ionization isomers. Okay. So when the counter ion in a complex is itself a potential ligand and can displace a ligand, which then it is displacing a ligand, and that ligand is SO4 in this example. It is displacing SO4, and that SO4 is becoming a counter ion in the second part. So that ligand which then become a counter ion. Okay, so those two are called as ionization isomers of each other because both have the same formula but different counter ions. Okay, shall I go for the last type? Shall I go for the last type? So what is the first type? First type is linkage. And the second type is coordination, where you have two square brackets for one compound. Third is ionization. Now the fourth type is called as solvate isomerism. So this is the last type of structural isomer. Okay. So what is solvate isomerism? When solvent molecule in a complex is itself a potential ligand and a ligand which then become counter ion. And this solvate isomerism is also called as hydrate isomerism when the solvent is water. Okay, it is also called as hydrate isomerism when water is a solvent. So now let's take an example. This is the example. And we have H2O outside the bracket, and that H2O can act as a potential ligand. So what it will do, it will go and displace the Cl which is there inside the bracket. So that Cl will come out and this H2O will go and take the place of Cl. So if these two jumps like this, what we will get? Already 5 H2O is present inside the bracket. Now it is also coming. So totally 6. Now this Cl is coming out. Already we have 2 Cl outside. So if this also comes out, I will have 3 Cl outside the bracket. Okay. Now this Cl is the ligand, becomes a counter ion after displacement. So these two compounds have the same molecular formula but different arrangement. Okay, so those two compounds are called as solvate or hydrate isomers of each other. Is it clear? Can you able to understand? If water is displacing some other, it is called as solvate isomers. That's all. Clear, students? Any doubt from this? No doubt? So this is all about the structural isomerism. Now the second category of isomerism is stereoisomerism that we will discuss in the next class. Okay. So today we have discussed the nomenclature and the structural isomerism alone. So in the next class we will discuss about stereoisomerism and then we will go on with the valence bond theory. Okay. Any doubt for anyone? Do you have any doubt? Any of you have any doubt from today's session, students? No? Okay, then thank you so much. See you all in the next session. Take care. Bye bye.